great to have Dr. Tuan visiting us from UCLA. He actually got his PhD from UCLA in 2010, and then spent some time at UC Irvine, where he was the TMT postdoctoral fellow. So he spent some time thinking about one of the first light instruments for TMT, the infrared imaging spectrograph. After that, he moved to Canada at the Dunlop Institute, where he was the Dunlop Fellow. But I guess he decided California was just way better than Canada, and went back to UCLA. So he's now an assistant research scientist there. And so yeah, he's an expert in all things related to the Galactic Center, and has also spent some time thinking about the dynamics of nearby Milky Way dwarf galaxies as well. So yeah, welcome.
Thanks. Thank you for the invitation and a chance to talk to you about the center of our galaxy. So it's a subject I'm pretty excited about. Today, in particular, we're talking to you about the origin and the structure of the nuclear star cluster in the galaxy, and how we can study them, one star at a time. This seems kind of tedious because there's like millions of stars in this cluster, but actually you can get a tremendous amount of data if you can study stars individually. Now, this work is done in collaboration with a large number of folks, both at UCLA and elsewhere. To begin with, what do I mean by the nuclear star cluster at the center of a galaxy? And this kind of shows that this is what the discovery of the nuclear star cluster basically in the late 60s, when the first infrared detectors were available on the sky. Beckley and Neugebauer basically used it to scan the sky near the center of the galaxy, and they found this is their hand-drawn plot of the brightness as a function of distance from the center of the galaxy. So here is the scale, so it's about 7 parsecs or so across here. And they noticed that there's a large concentration of light at the center of the galaxy. Other seeing limited observations, like this one from Haller et al. In 1996, saw that there are lots of really bright stars at the very center. Now this is a much smaller scale. And these stars turn out to be really interesting. I'll tell you more about those soon. But what does the sort of more modern view of the galactic center look like? This is a Spitzer image now of the center, about 100 parsecs now or so on the side. And you can see that there's this really bright concentration of light, which is where that infrared detector was looking at. And there's a very compact star cluster in the center. This star cluster is the densest star cluster that we know of in the Milky Way. And it has a half-light radius of between 5 and 8 parsecs or so, and it has a mass of about 10 million solar masses. So it's by far the most massive cluster in the Milky Way as well. But let's try to zoom in further into the center of the cluster. So you now take the Spitzer 4 microns and zoom into about the central, maybe 10 parsecs. You can see that at Spitzer resolution, you can't really see very much. And so we can switch to HST. This is a WIPC3 IR image of the nuclear star cluster. Now you can start resolving lots of individual stars. You can see that there's lots of patchy extinction, so that's a problem that you got to get rid of. But then what I'm going to talk about today, actually, is the very center of the cluster. And if you zoom in further, even at HST, now this is about 2 parsecs on the side, so even at HST resolution now, it's hard to see individual stars. So you can see some of the brightest ones, but they're starting to be basically all blended. So actually what we need to do is go back onto the ground and observe with adaptive optics. So I like this picture, not only because it tells you where the galactic center is, but that it shows adaptive optics has really come to be routinely used. And this is the 4 telescopes on Mauna Kea that have laser guide star adaptive optics. And this was taken last year. So these are the 2 Keck telescopes. This is the Subaru telescope, and behind the Keck telescope over here is Gemini. So they were all observing the galactic center. The reason
together or competitively?
Together. So, well, okay. But these 2 telescopes were, the time for these telescopes was Andrea Ghez's times from UCLA. My program was being observed at Gemini, and then a Japanese program was being observed at Subaru. Yeah. They were observing different things at the galactic center, so it's not really a competition. Anyway, the way the adaptive optics work here, just very briefly, the reason why we have these lasers is that it makes it makes a guide star, an artificial guide star in the sky to track the atmospheric turbulence. And so that's how you would correct it. Normally you could use a bright star as well, but that kind of limits the area of the sky you can observe. And so that's why the lasers were so powerful when they came online. So now with LGSAO, what does it look like? Now I've zoomed in really close. Now this is the central, about half parsec of the galaxy. And this is a 2-micron image of the galactic center. And between these two little arrows is actually the location of the supermassive black hole Sagittarius star. So it doesn't look very impressive compared to all these other bright stars. But we know it's there basically from kinematics of the stars nearest the black hole. Okay, but today I want to talk to you about the nuclear star cluster itself. And there are two main questions I want to address. One is the physical properties, the formation and evolution of the nuclear star cluster. Since these star clusters are actually found in many galaxies, especially galaxies like the Milky Way. And so we'd like to understand how its connection to galaxy formation and how it interacts with the star cluster and a massive black hole. So the Galactic Center provides a great testbed for dynamical theories, basically, because you can see individual stars and you can perceive how they behave around a black hole. Okay, since I'm an observer, I kind of go through this in terms of what I can measure, and then how these measurements connect to the science. So that's kind of the way I'm going to structure this talk. So let's start out with just images and spectroscopy. So with imaging, you can get the positions of stars from measuring astrometry, and then you can get the brightness of stars. From spectroscopy, you can get the spectral type. So the reason we use spectroscopy is that we really, at the Galactic Center, need it to differentiate between the different populations of stars. So there's two main groups of stars at the Galactic Center. There are these very young stars, which are like basically O and B stars, and those are about 4 to 6 million years old. But actually, a lot of the stars are really old stars, so over a giga-year-old. They're like the late-type giants. So this is a sort of theoretical color magnitude diagram of the Galactic Center with K and H minus K colors. So you can see that they have about the same brightness, the young and old. And theoretically, you should be able to separate these two types of stars just with photometry. But you can see that their colors are actually very, very small, just like a tenth or so of a magnitude. And so, unfortunately, the Galactic Center, like I showed you before, had really variable extinction. So you can get extinctions of greater than magnitude over just several arc seconds. So using colors is not enough, basically, to determine the types of stars. So that's why we painstakingly use integral field spectroscopy all over the cluster. And this is an example. This is an OSIRIS, which is the integral field spectrograph on CAT. And it has a plate scale about 35 milliarc seconds. And this is a collapsed data cube, so you can see basically the image of the star, and you get basically a spectrum of every pixel. And here I just showed two examples. So this star has a spectrum that looks like this. And you can tell that this star is young because it has pretty strong hydrogen absorption lines and basically nothing else. There's some helium lines as well. And the reason for these hydrogen lines, of course, is that it's really hot. And so that's how we can tell that it's a B star, basically, and young. On the other hand, a star like this is a red giant. You can tell that there's many, many other lines. There's really strong molecular lines like CO, but in this wavelength range, there are these very strong sodium features that you can see. So you can just by eye, going through all these hundreds of spectra, try to classify these stars. And what do we get? This is an image of the Galactic Center in the back now, but I've now overplotted symbols to indicate what type of stars they are. So in red are the old stars, these red giants, and then in blue are the young stars. At the center of the galaxy is this little diamond here. You can and these little blue boxes are basically each little postage stamp integral field spectrograph observation. So you can tell this is a time-intensive effort to map every little square of the Galactic Center this way, but you can get spectra of a lot of stars. So you can immediately tell from this image that there's a lot of young stars, and they're preferentially near the black hole, right? So this has been a long-standing problem or question in the Galactic Center of how did these young stars get there? You would typically, when you think of star formation regions like near the sun, you think of a molecular cloud that collapses and then fragments to form stars. But near a black hole, if you put this molecular cloud there, it would be completely ripped to shreds by tidal forces by the black hole. But nevertheless, there are stars there. How did they get there? There are two main theories about this. One is that maybe they didn't form at the very center, but they formed further out in a cluster, and then that cluster migrated toward the center of the galaxy. So this is a cluster infall. In such a scenario, you kind of expect to see like a trail of stars that comes to the center. The other idea is that maybe Sagittarius star, while it's very quiet now, in the past might have had a large accretion disk, more comparable to AGNs. And this large accretion disk can have enough mass in its disk plane that it can collapse due to self-gravity and then form stars in a disk, for example. And so this is what we're calling in situ star formation. One of the predictions from in situ star formation, because it's so different physically than cloud fragmentation, is that perhaps you can get your products of star formation might be different. So the masses of stars you get might be different than a normal neighborhood. So this is where the initial mass function comes in. So in this prediction by Vanella and Rice, they predicted that the distribution of mass should look like this. And if you look at mass distributions in the solar neighborhood, this looks very different. So in the solar neighborhood, the IMF is called saltpeter, and that means it's very steep. So at lower masses, there are many more stars than at higher masses. But here, it looks kind of flat. Of course, these simulations can have very large range in IMF, actually, depending on the input conditions. So it is helpful to observe young stars at the Galactic Center to test this. Some of the earlier observations of AO observations of the Galactic Center suggest that maybe the mass function at the Galactic Center is actually really super steep. So the plot to look at here is this blue curve. So this is a luminosity function now, not a mass function. So that's going to be important because we can only observe the brightness of the star. We can't really observe the mass. So this is basically number of stars as a function of magnitude. So you can relate the magnitude of stars to their mass if you have some sort of stellar evolutionary model and atmosphere model to tell you how to interpret that. And when Barker et al. Did this, they found that the mass function had a power law of 0.45. So this is much smaller than the saltpeter power law of 2.35. This is one of the strongest cases for a varying initial mass function that's ever been measured, basically. So one would like to look more into this, and that's what we sort of set out to do. And immediately one runs into this this question of observing bias, essentially, because here's kind of how we should show this. When I was showing those spectra earlier, right, they are for pretty bright stars, so it was very obvious by eye how to classify whether it's young or old. But as you get to fainter and fainter magnitudes, obviously this becomes harder and harder, right? This is what we mean by completeness. So with imaging, we can see we're pretty confident we're pretty complete because the images are deep and very high resolution. But with spectroscopy, because of the initial time required, we can't get very deep. So that means at a K of about 15.5, we can only spectral type about 50% of the stars that we can see from images. So the question is, how do we correct for this completeness, right? And it really matters to your mass function because your faintest bin and basically the bins at your end is going to make your slope. And so whatever correction you apply is going to affect your slope a lot that you infer from the mass function. Okay, so there's basically some choices that you can make for completeness correction. Here are some ones that might be possible. You can assume that the unknown sources have the same fraction of young versus old as the ones that you've identified, right? So in a given bin, if you see like 5 stars that are young and 10 stars that are old, then the number of unknowns should have the same fraction. But that's one possibility that you do. Another possibility might be that, okay, so But this assumes that you have the same sensitivity for the detected versus the non-detected source, right? The other possibility might be that you just assign equal probabilities for young and old for this population that you don't see. Neither of these cases is particularly satisfactory in terms of completeness correction, right? And mostly it's because it doesn't take into account all the information you know. So even though you can't by eye immediately tell whether it's a young or old star, there's still information there, actually. And there's information from other parts of the, there are other pieces of information you can add in. So one example is, one way to incorporate these pieces of information is that we can just use a little bit of Bayesian inference. So you can classify the stars by adding more and more pieces of information. And with the Bayesian evidence, it's a pretty natural way of doing it, because basically what it's saying is, what is the probability of observing your particular star given your measurement, and then some priors on what you expect a young star or old star to look like, right? And then you can compute the Bayesian evidence for whether this star is young, and you can compute the Bayesian evidence whether this star is old. And the ratio of this tells you which is more likely, essentially. And to show this a little bit of an example, let's just take one line for now. Let's take the equivalent width of sodium. So you saw that there was a strong sodium line for old stars, right? So our prior that is this dash curve here. So we're saying that our knowledge of the old star is that they have a distribution of sodium equivalent widths that look like this. Okay, and then for young stars, because there's no sodium, and it's just measurement, or you can just have a distribution of sodium that looks like this in dash blue. So now let's say you've observed a sodium line that has this equivalent width and this error. What is the probability that this star is old given this observed sodium line? So basically you just work through this equation, and basically it's the area under the curve here, which is the red. And then you can ask, what is the probability that the star is young given this observed sodium line? So obviously this observed measurement doesn't change, but the prior changes, and so you have a lower probability. So for this star, you would immediately say it's a much stronger probability of being old than young. But we don't. But we're not just limited to the sodium equivalent width, right? We have other structural features like the hydrogen line too. Another piece of information we have is actually the position of the star in the field. I don't know if you noticed, but in the previous plot when I showed you the spectral identifications, young stars are really concentrated toward the center. So if you're far from the cluster, you're statistically much more probable to be an old star than a young star. Okay, so now that we've developed this sort of method, we can apply it to the stars. But before we do that, there's another piece of information that's not included, which is the effect of confusion. So the galactic center, because there's so many stars, actually, where you are can really affect your sensitivity to being detected. And this is kind of shown here. See, these green circles are stars that don't have spectral types. And you can see that, for example, this one is like really close to this bright guy. Some of them are pretty isolated. So the way we take account of this is we do star planting simulation. So we plant randomly old and young stars near every unknown source, and then compute the Bayesian evidence for it being young and old. This way, we can translate our Bayesian evidence to an actual probability of the star being young or old.
Can we back up 1 minute?
Yeah.
Isn't it more proper to say that if you have 100 stars and this separation criterion, then when you apply the Bayesian information, well, it'll separate them into two groups, right? And so this group would give us some mean properties and the other some different value. Do you really need to say that you can identify individual stars? This one individually is old or young.
Yeah, that's right. You should be able to compute the probability of a membership. So it's the same procedure as finding the bulk population, right? If you know the bulk population, then you know that given some set of measurements, they statistically should have some probability of being on this population, this population. So every star in this sample, basically at the end, is going to have some probability of being old, some probability of being young.
So what's considered strong possibility? What kind of number? 0.9, 0.999?
Oh, I guess it doesn't. we just end up in our analysis using the probabilities. We don't actually, like stars are not, well, some stars have like 100% essentially because the evidence is so strong, but these like green stars, for example, a lot of them don't have 100% evidence. You know, it's like 75% or something. So we consider the actual probability of the star for all the subsequent analysis. So we don't like have a straight cut basically. Yeah. So this is actually what this plot is. So this, if we just take, if we now plot a histogram of all the stars now weighted by their probability of being young, this should provide the completeness correction we want at the faint end. So this is what this blue plot is. So in purple is our measured luminosity function, and you can see, well, we're pretty complete up to about these last two bins, so there's not very much completeness correction does. But then these last two bins is basically where the significant completeness correction comes in. In black here, I've plotted this other result that I showed earlier with Barco et al., which found a really steep mass function. This is their completeness corrected curve. So you see with the completeness correction, this is much steeper now than the other mass function. Actually, even without completeness, it's still like pretty sort of steeper. So then we can ask, given this luminosity function, how does that translate to slope in the initial mass function? So to do that, basically what you would do is generate lots of star clusters from your knowledge of stellar evolution and the stellar atmosphere. You can predict, given an age, what the luminosity function should look like. And so basically this is what this probability distribution is it's marginalized over the other parameters except for IMF slope. And you can see that it's about it peaks about 1.7. So it's still flatter than saltpeter. So I think the galactic center, the initial mass function is flatter than saltpeter. I mean, more top-heavy basically, but probably not as top-heavy as this other result. Right now, I'm a little bit unsure why there's such a big difference actually, but okay. The other thing you could do, which is a little simpler than doing the mass function, is to look at the density profile. And this is basically surface density of young stars as a function of projected distance. One of the surprising things, which we didn't realize until basically this year with really enough radio coverage, is that the star cluster abruptly truncates at half a parsec. So before, because there's not very much spectroscopy was done, like we're slowly basically expanding our radii in spectroscopy, and we finally got beyond about half a parsec, and then suddenly we like basically see no young stars. And I think this really like disfavors the infalling cluster hypothesis, because you'd expect to see this trail of stars, like I said before, and this truncation is what you'd expect maybe if you had star formation in a disk. But it's also kind of surprising. It's like very small. It's like half a parsec. It's a very compact information. Okay, so I've talked about the young stars, but actually the old stars is the bulk of the population. And what's interesting about the old stars, one of the things that you can immediately try to check is, do the old star cluster look like they should around a massive black hole? Right? This is one of the very early theoretical predictions for how star clusters should be around black holes by Bacall and Wolf. And the theory is pretty straightforward. The black hole acts as a sink for stars. So stars occasionally fall in the black hole and gets eaten. So that means the star cluster must lose potential energy, right? And given enough time, the star cluster should, this loss of energy needs to equilibrate somehow, right? When the star cluster comes to equilibrium. And the way it does that is by having the density be higher at the center. So this is Bacall Wolf's prediction, density as a function of distance. With a black hole, you should get a slope here, and it's about 7/4 or so in the power law. And without a black hole, it should be really flat. Okay. So why do we care actually about whether this exists or not? One of the reasons we care is that a lot of simulations assume a Bacall-Wolf slope when they simulate things around supermassive black holes, such as the feeding of supermassive black holes. Also, predictions from gravitational in-spiral often need background objects in spiral, and so you need a density of them. it was also initially thought of as a way of maybe detecting black holes without stellar kinematics. But in order to test this, you need a confirmed black hole and you need a dynamically relaxed system. The Galactic Center definitely has a black hole. So these young stars are about a giga-year-old, so they, or older, and so they're kind of on the regime of being dynamically relaxed, so you can potentially test them. But what we see is really different. This is the density profile of old stars. So you would not have thought there's a black hole at the Galactic Center if you looked at this. It's really, really flat, and in projection anyway, so this projected density profile as a function of distance. But it's a little bit tricky to interpret a projected density profile, right? Because what you really want is the three-dimensional profile of the star cluster. And here, this is just an illustration of why it's hard to use projected density profiles. So if you look at the 3D profile now, so if you have a slope of about 1, in projection it gets shallower. And then actually if you have anything more shallow than 1, in projection it's just completely flat. So using the projected density profile alone, we can't rule out basically many of the density profiles. So in particular, it'd be interesting to know whether it has a hole in the distribution of the stars. Okay, so that means we need to add more information. So, so previously, basically the information I talked to you about are all single epoch information. But you can take images more than once, right, at the Galactic Center and measure velocity. So this is what the UCLA Galactic Center group has been doing for the last 20 years or so. And so there's very good velocity measurements now in the plane of the sky. And then with your spectroscopy, you can get easy. So you have now 3D motions. Here's the same plot, curiously, except now I put velocity vectors on top of the star. You'll immediately notice that, like, even if you didn't know where the black hole was in this image, you could probably guess, right? It's here, where like the velocity vectors go crazy, and that's where the dispersion is the highest. In radial velocity is a little bit harder to show. So this is basically the same map, but doing nearest neighbor color to show the radial velocity. So for the old stars, it looks like this. It's pretty normal. There's not really any structure. But then, if you look at the young star, voila, it's very different. So I'm just zooming in this region for the young stars. You immediately see that there's a disk, right? So the velocities of the young stars are in the plane of sky this way, and then out of the plane of the sky this way, and in the plane of the sky that way. And in fact, if you put together the proper motion and the radial velocity for the young stars, you can make a dynamical model of the cluster by just getting the orbits, essentially. So this is what this movie is. I like this movie. And in the colors here, in blue, these little green points are the young stars at the Galactic Center. So now we're zooming out of the center of the galaxy. And then as you come out, you should start seeing by eye different kinematic features. So in the very center, the orbits are pretty isotropic, but then as you get further out, like the disk becomes really apparent, right? And this is the young stellar disk. Okay. So it was a cool movie, but let's do it more quantitatively. So what you can do is, with 3 velocity vectors and a 2D position, you know what the orbital plane of the stars are, right? So you can plot the orientation of the angular momentum vector of the orbital plane on the plane of the sky. So this is a projection as if you're standing on top of Sagittarius star and looking at the sky. So basically there's a large concentration of angular momentum vectors in this direction. And that tells you that there's a disk. So Silvana Yella did this analysis, and she did some simulations to show that if you put all the stars together, about 20% of the stars are consistent with being on a stellar disk. So this is pretty good for the in situ disk formation hypothesis, right? Because there's a disk. But the tricky part is, what is this? Only 20% of them are on this disk. This is kind of surprising because where did all the off-disk stars come from? Did they come from being ejected off the disk? Were they formed in a different star formation event? Like, what's going on? And right now, we don't really have answers, but I think the in situ formation hypothesis is probably likely. Okay. As for the old stars, we can also do a dynamical model. Remember, the thing that I was interested in for the old stars is what the true 3D density profile of the old stars look like, right? And with the 2D projections alone, we couldn't tell, but with some kinematic information, we can hope to. So we just did a pretty simple genes model of the cluster. So in genes modeling, what you're basically relating is the tracer profile over here, like this row, and the second moment of the velocity distribution to the potential. And the tracer profile is the one that we want to figure out. And so we've parameterized it as a power law. We allow for some velocity anisotropy. And then we let the potential be free, but mostly it's dominated by the black hole, right? We're in the central half parsec or so, and the black hole steer influences out to about 2 parsecs. We also let the distance to the galactic center to be free. So these are basically all our parameters. We assume spherical symmetry and no rotation in the inner half parsec. Okay, so typically what one can do is now bend up your velocity dispersion as a function of radius and fit these parameters. But in the spirit of trying to use as much data as we can, we instead use a likelihood analysis. So what this analysis is asking is, for every star, you can ask what is the probability of observing that star at that location with that velocity given your data model parameters, right? And then with the magic of computers, you can just combine all the likelihoods together, and then using a Bayesian sampler, iterate through all of the, look at what the parameter space looks like for your model parameters. Okay, so the posterior distributions for inner slope is what I was interested in. This is now marginalized over the other parameters. And here, it peaks basically around 0. So it's basically saying the most likely, most probable answer is that the density at the galactic center is really flat, truly flat in 3D. But you'll notice that there's still a tail, and so some, like a hole, could still be emitted. The other kind of interesting component is the velocity anisotropy of the galactic center. And this seems about flat. This might help you. I originally was trying to do the velocity anisotropy because I wanted to see how the core was created. One of the ways to create a core at the galactic center is you had an infalling second black hole, right? Comes in, it'll kill all the radial orbits, right? That crosses this orbit, and so you should be left with some tangential anisotropy in the center. But perhaps that fell in much longer ago. Okay. The other interesting thing coming out of this modeling is that you can get the mass of the black hole, and this is the galactic center. So this is the joint probability distribution of mass of black hole and R naught. It's approximately consistent with the stellar orbit. And this was interesting because a lot of work has been done in the past using velocity dispersion to constrain the black hole to the galactic center, and their mass has always come low compared to the mass from orbits. It was usually around like 2 times 10 to the 4 million solar masses, whereas the orbits we're getting like 4 times 10 to the 6 million solar masses. I think with this analysis, we figured out why. The reason is because in the past, a lot of those velocity dispersion measurements assumed that the density profile was Bacall-Wolf, essentially. So basically what you're saying then is you're putting a lot of stars close to the black hole, and because you have a low velocity dispersion measurement, you would have a lower black hole mass. But if you fit for the velocity, for the density profile as well, then you get that the density profile is actually really flat, and so the mass goes up, basically. So the interesting thing actually about the cluster method is that it has a different degeneracy in M versus R naught, and so you can combine it with the stellar orbits and get a better joint fit for like R naught, the distance to the galactic center, and you can improve by over 30% actually if you add the cluster in. This parameter is pretty important because it sets a lot of galactic distance scales. But right now we're kind of dominated by systematic uncertainties in actually both the orbit and the cluster method. Just very briefly, there's another way you can constrain the density profile, and that's directly with accelerations. So if you have enough time, you should be able to see stars accelerate in the sky, and then you just use Newton's laws to figure out where in 3D those stars are. So this is a project by a grad student at UCLA, Sham Chappell, and she basically made these 3 bins of stars at the Galactic Center. And so her work is going to come out pretty soon. But this is a different way of getting the density profile. Okay. So I've talked a lot about the current structure, but how do we figure out about the origin and evolution of the cluster, right? So there's another additional piece of information you can get from the data, and that is you can fit the spectrum with stellar parameters, right? You can get effective temperature, surface gravity, and metallicity. So I'm going to use m over h to symbolize scaled solar metallicity. And this is a logarithmic unit. Okay. In pretty brief, there are 2 main theories about formation of nuclear star clusters now. So these large nuclear clusters at the center of galaxies. One is they could be formed by the collection of globular clusters. So this is a simulation of how globular clusters can fall in their center and make a giant cluster in the end. Another idea is that perhaps they're formed from gas in the disk that funnels in. And in that case, you might perhaps see like a disk if the star cluster is young enough, basically. So this is what Seth et al. In 2008 saw in this nuclear star cluster in NGC 4244. Okay, so how would you differentiate between these scenarios in the Galactic Center, right? You could use schematics, but the one that I'm going to talk about is with metallicities. So if you think that globular clusters are going to form the nuclear star cluster, one way to check would be to see whether their metallicies were consistent with globular clusters that we see today in the Milky Way, right? And another important point about knowing the metallicity is that it really affects how you think about the star formation history of the Galactic Center. So remember, we had to translate everything that's done at the Galactic Center. We do luminosity functions is what we measure, right? In order to translate the star formation history to a luminosity function, we need to go through these stellar evolution models. But the stellar evolution models are very sensitive to metallicity. So for the young stars, it was just formation at one time, like 4 to 6 million years old, and so we use solar. But actually, these old stars, they may have very different metallicities. And this is just showing that. This is an HR diagram, basically, of isochrones of the same age in the same population, but just changing metallicity. So you can see that the inferred brightness would change a lot depending on metallicity. So for a long time, we thought that the nuclear star cluster should have about solar. And there are several lines of evidence for this. So if you look at the metallicity gradient in the galaxy as a function of distance from the Galactic Center, it sort of increases, and at the center, it looks like it could be about solar. About 12 stars have been measured at the Galactic Center, and they're basically this black histogram and this red histogram. So these other histograms are the inner bulge. So this seems pretty reasonable, but we'd like to get a larger number of stars to really map the metallicity. And the way we're doing this is we're going to do the we're going to fit the spectra using a spectral grid. So we use the marked spectral grid, which goes from about 2,000 Kelvin to 7,000 Kelvin, and a log G of minus 0.525, and a scale metallicity of minus 3 to 1. So this is like 1,000th solar, and this is 10 times solar.
How do you scale the helium abundance?
It's just strictly scaled solar. So alpha over H is 0, essentially.
Okay, but the helium abundance is, you're saying, is it delta Y over delta Z of 3? What do you?
That's right. Yeah, we assume solar. Yeah, the relative. Yeah.
That is an assumption.
That is. Yeah, you're right.
You're not measuring the helium abundance.
That's right. Yeah, it's just strictly scale solar. Yeah, and that is one of the things I'd like to do in the future. But so this is just one of the tests. This is the solar spectrum in black, and then our best fit is in blue, which you can't really see, and then the actual model for the sun is in green here. But the sun is not really representative for most of our stars, so we'd like to do a better test. The other test we did was to look at the specs infrared template library, and they basically this template library are really bright stars in the near infrared that the SPECS telescope observed, and a lot of them have literature values for TEF, log G, and metallicity. And so we used our models on those stars to see if we're consistent. You can see here is our fitted M/H versus the reference. And they're consistent to about 0.3 dex or so. I think this is okay because one of the interesting things about metallicity is that everybody has a slightly different way of measuring metallicity. And so in the literature itself, some stars can have dispersions of metallicity by 1 dex, for example. TEF also works pretty well. Log G is kind of horrible.
Sorry, can you
yeah.
explain that last statement a little bit more? A star having a metallicity spread of 1 dex? I'm confused.
The measurements have a spread of 1 dex, yeah. It's just because people have different methods of measuring metallicities, and they often also have different correction factors to their metallicity measurements. Because various methods have different biases, essentially. And so for some stars, huh?
They're not 1 dex biases.
I don't know why, but that is just true. You look at the literature; some of these stars have very large dispersions.
Chris knows the literature pretty well.
Yeah.
No, it's a question, not a
Yeah. I mean, a lot of these are better. I think our sample in general has a dispersion index about 0.3, a little bit, maybe a little bit less than this. Yeah. That's right. Okay. Log G is really bad, like I said, but it is not so bad for what we want to do because we know these are red giants, so we can limit the range of log Gs that they could be. Okay, so we had to do this fit simultaneously because there were correlations between a lot of these parameters. So for example, log G and TAF are correlated. And that this is basically joint posteriors for the parameters we fit for, including the radial velocity.
But a joint fit doesn't mean you get rid of the correlation of the parameters.
That's right.
Just
Yeah.
a
So
joint fit.
that's why you have like this essentially. Yeah. But actually the width of these probability distributions are actually much smaller than the spreads that you see here. So our uncertainties are totally dominated by systematics.
I'm sorry, just one other question. You say these are red giants, but gosh, most of them look like subgiants in your log G plot. If those are
Yeah,
actually
some of them could be. The brighter sample could be subgiants. Yeah. It doesn't change their metallicity very much though. I guess that's the important point.
I mean, it could change it by 0.2 dex.
Yeah, but our uncertainties is already.
It was a systematic shift, so
It's a systematic.
you're constantly getting log G's wrong in a certain direction when you're systematic.
Not according to this. Well, it's hard to know for our population, but for this sample, these things are not correlated with worse dispersion in this. Do you know what I mean?
This doesn't prove there's no correlation though, because the spread can hide the correlation. So, I mean,
That's true. Yeah, that's actually absolutely true. Yeah. So what we would like is some reference stars that are like really well pinned down, right? And observe those. Yeah. Okay. So one of the things that surprised us was that there are definitely some low metallicity stars in the Galactic Center. This is in black is the stellar spectrum, and then in these colors are different fits. So the best fit is blue. This is going to be really difficult to see, I guess. And then in these other colors, we've increased the metallicity to show the effect of increasing metallicity. So you can see that, for example, like these sodium lines are much better fit with a low metallicity. And then there's some iron lines here, for example, like this iron line like almost doesn't show up. That's fit better by lower metallicity. As you can see, as you increase metallicity, it would predict that these line strengths should have increased a lot. And the other thing we found is there's very large metallicity variations in the galactic center, right? And I showed here 3 example stars. One is low metallicity, about a tenth solar. One is about solar, and then one like really super solar. The blue is the best fit, and then the green is if we fix metallicity to be solar, but let the other values vary. And so you can see for this star, for example, like this iron line is like much better fit by low metallicity. So is these sodium lines. You'll actually also immediately see that as you get to higher metallicity that suddenly lots of lines appear that are not well represented by the model. And so this is why we think that just at about 0.3 solar metallicity and higher, there's a systematic in the model that's probably going to dominate our measurement for these high metallicity stars. But I think we can, I'm pretty confident in the fact that there are a large spread in solar metallicity at the galactic center, and larger than that was seen before in the past. This is, and so this is the histogram. Like I say, this peak at really high metallicity it's probably going to move because they have, we're not really sure about where the systematic error. It could be the line list, it could be how those spectra are calibrated. There's not very many calibrations at super high metallicity. But what we're interested in more is like the fact that the metallicity seems to spread a lot, and also that there are this population of low metal stars. So about 6% of the stars have metallicities below minus 0.5 dex. And in particular, in terms of this globular cluster thing, the metallicities below about 1 or so is typically what you see for globular clusters. And so if we think that, if the scenario is that globular clusters like we see today was what makes up the nuclear star cluster, then they probably make up a very small fraction of the nuclear star cluster. Of course, that doesn't rule out the fact that if globular clusters had some like metal-rich globular clusters for some reason preferentially fell into the galactic center, then
Well, there are metal-rich globular clusters towards the galactic center. They're preferentially there, so
yeah,
that's
but
exactly true.
They are, even the most metal-rich, like Tuan 5, it's below solar, right?
Not
so,
much.
Yeah, yeah. And there's not like, there's not 10 million solar masses of them, I guess is the point. There's far more of the other types, yeah. Okay, so I mean, one of the other things you'd like to do immediately right now is to measure the other elemental abundances, right? Like the alpha abundance is really important to measure because that varies across the galaxy, and then individual elemental abundances could tell you maybe from where in the galaxy these stars come from, right? So the spectra that I showed you today are all medium resolution spectra, so it's very difficult to get like individual abundances from medium resolution spectra, and so we're in the process of trying to get high resolution near infrared spectra. But that's hard to do at the Galactic Center because you need both AO and high resolution near infrared spectroscopy. So we're trying, but we'll slowly get there, I think. Okay, so I guess to summarize a little bit, each new dimension of data has really increased our knowledge of the Galactic Center, and it's really surprising, actually. Every time we add new information, like there's something surprising that comes out. And I'd like to end my talk a little bit about the future at the Galactic Center. So this is a simulation of what the next generation of very large telescopes will see at the Galactic Center. In particular, here is TMT. So this is Keck. So this is using data we have today. And you can see this star is SO2. It's the one that helps us measure the mass of the black hole. And it goes around in about 16 years or so. And this is TMT. Basically here are orbits of stars that are under like 20 years that we'd expect with TMT. So with TMT, we expect some stars to have orbits of as few as a few years around the galactic center. So this will be the region where it can test like things like general relativity at the galactic center from just watching the precession of orbits there. Stellar population-wise, it's going to really help us. This is the current image of the galactic center. There's about 3,000 stars in this image. Simulating the depth of TMT and this larger field of view, because it has better AO correction, there's about 300,000 stars now in this. In terms of parallel population, what this gives you is it lets you get to the main sequence. It lets you, in fact, you can get to the pre-main sequence for the young stars. So you can get below a solar mass spectroscopically at the galactic center. Right now, we're up here. By the way, all the spectra of those young stars I showed are 10 million solar masses or more. And so to do real stellar population work, you want to go really down here where all the stars are. And the other cool thing is we can do what we do for the galactic center in M31. So while M31 is about a factor of 100 further away, the black hole mass is also quite a bit higher. And so you should be able to measure individual proper motions of stars in M31 as well. Yeah. So thanks very much.
Could you kind of go back to your first nice synthetic spectrum fit?
This
That one. Yeah. What? These are cool stars, right?
They are, yeah.
And they are giants, right? I mean, their luminosities you must know well enough. I mean, just because they're brightnesses. So they're probably not. I mean, they probably have to be giants, right? But you're using log G of 4, which is a subgiant at best, almost to the main sequence. And I think what that does is if you assume, say, log G to 1.5, appropriate to 4100, if you claimed it was a giant, then that increases the column density, makes your predicted spectrum much deeper, which you would have to lower the metallicity to compensate. So I think some of the metal richness will go away if you assume these things are giants, I think.
It's super complicated. So the correlation between log G, so it does correlate a little bit, like you can see here, right? So it can, as it gets more shallow, perhaps it probably will increase the metallicity a little bit, but I don't think it can increase it to the. I don't think it can get back up to solar.
He said the opposite.
Yeah, he said the opposite. It's decreasing your metallicity.
Can you show us the
By
explanations for
reducing
the-
your log G, your metallicity goes down.
And
That's not what the correlations are saying.
Your Fe to H, your mean is like -1,
It's 0.1, 0.9-ish.
Yeah.
but then your histogram had them super solar, didn't
Wait, sorry. This is for an individual star,
it? Yeah.
but that histogram is not.
Oh, for an
I'm
individual.
utterly confused.
These are all the possible solutions for an individual star.
Yeah, for one star.
Oh,
Oh,
for
oh, okay.
So for this
Yeah, yeah,
particular
got it.
star,
Got
you
it,
can
sorry.
see the
I'm
correlation.
sorry.
Yeah, yeah. So, yeah, I mean, I think it's definitely worth investigating what's going on in log G, yeah, right now.
To follow up on that, was log G then allowed to float freely, or was it restricted to sort of linear form?
Oh, so it was. Oh shoot, I don't have that plot. It was restricted to a range that matched the luminosity. So, so I think for these particular stars, you expect log G's of between 3 and 4, given their stellar evolutionary models. So, so what we do is we take the K luminosity that's extinction corrected, and we ask of the different cell evolution models that work. Basically, I think I'm using like 1 gig a year to 10 gig a year, and saying what log Gs are possible given that observed magnitude range. And that's what we use as the fitting like prior range.
Any other questions?
So, you said you did not constrain the cusp to be recallable. Did you have a best fit value for your cusp, or is it just?
Yeah, so I think in the genes modeling, what we're this is the best. I think this is our best constraint, is that it's around 0-ish.
That's the like the three-dimensional slope. So
Yeah,
that's
that's
7/4
right.
of the ball.
Yeah, so like 7/4 is like way not possible, I guess. But
If you like keep the orbits isotropic, does that break this degeneracy completely?
so if you force velocity anisotropy, then this thing shifts up a little bit and it cuts off a lot of the tail. So yeah, but the answer is still sort of consistent within 1 sigma between the two.
But it's not consistent with all that.
Yeah. Yeah, I think we can rule that out pretty strongly.
Just one suggestion, have you thought, or just a question, have you thought about stacking your spectra? Once you get, say, these things are all looking like the same kind of star. Have you thought of just adding up the spectra and getting signal noise better and repeating your analysis?
No, we haven't, but that's a good idea.
It's worth trying.
Yeah, one of the problems with stacking spectra at the Galactic Center is that they have very large velocity dispersions.
Yeah.
So you generally have to interpolate
Yeah.
your spectra, and so that can sometimes
Right.
change the depth.
Anything else? Yeah, all right, let's thank Tuan again.
I didn't mean to be harassing you.
Oh, no,
I'm
great
Chris-
question.
I'm Chris Saint,
Hi.
and I do that, tell I do that for a living.
Is she coming?